Okay, here is Jeff, the math magician.
Thanks, Joe. So I'm Jeff Donatelli. I'm a research scientist in the math group at Lawrence Berkeley Lab and also in the Center for Advanced Mathematics for Energy Research Applications, or CAMRA. And today I basically want to talk about how we extend some of the iterative projection and phasing methods I talked about yesterday at the workshop to solve more complex inverse problems from experimental data. And so in general, what I mean by an inverse problem is basically that we want to reconstruct some physical object or model M that produce some set of measured experimental data D, and we also want to enforce various physical constraints C on that model. And so this can be essentially formulated as finding the model M that satisfies two kinds of constraints. You have a data constraint. So basically you want the model to correctly map to the measured data D, where this is done through some mapping F that you understand that does the mathematical operation of going from the model to the data. And you also have a physical constraint that you want to impose, where you want the model to satisfy various constraints C. And so there's lots of different examples of inverse problems. I guess the main one we're focused on today is determining structure from X-ray scattering, but this could also include things like constructing medical images from MRI data, inverting seismic reflection data, or tomographic reconstruction as well. And so I want to give a sort of quick recap of the basic iterative projection phasing methods, because this is sort of the framework that I'm going to base everything on today. So again, what we do in these iterative projection algorithms is so again, our goal is to find a model that satisfies these two kinds of constraints, a data constraint and various physical constraints. And so if we're going to apply an iterative projection algorithm to solve it, essentially what we do is we start by formulating what are called Bregman projection operators. So basically for every constraint C that we want to impose in the model, what these projections do is they take your current model, such as this blue dot here, blue, and the set of points consistent with the constraint, for example, this gray curve, and they project the model to the closest thing satisfying the constraint. And there's various ways to generalize this definition as well. For example, if for some reason your constraint cannot be satisfied, the projection instead essentially computes a least square solution to it. So in some sense, you can essentially think of these projection operators as some kind of nonlinear generalization of a linear pseudo-inverse. And so basically what I mean by that is if your constraint just had a single point on it, so there was a single solution, then the projection just turns that solution. It does the sort of inversion directly. If there's multiple solutions, then the projection returns the solution that's the closest one to your current model estimate. And if there's no solutions, the projection set finds the closest thing to being a solution, a least square solution. And so if you want to apply these projections to find some model that's consistent with multiple constraints, again, like in our example, the data constraint and these physical constraints, then we have something called an alternating projection scheme. And so basically to do this, you start with some initial guess x0 for your model. And then you form projection operations for each of your constraints, P of A to project on the A constraint and P of B to project onto the B constraint. And then all you do is you apply this iterative scheme where you take your current estimate at the nth iterate, xn, and then you project it to the closest point on the A constraint using the PA projection operator, and then use PB to project it onto the B constraint. And then you just keep going back and forth between those two projections until you converge to something. So graphically, this corresponds to the image on the right, where here, if we start at x0, you apply PA to project it to the closest point on the A constraint, and then PB to project it back to B, and then back to A, back to B, over and over again, until you eventually converge to something consistent with both constraints, in this case, this purple intersection point. And so when you apply these iterative projection methods to the phase problem, you get this. So you recall that the phase problem is, again, that we want to find a density rho that's consistent with two constraints. Our data constraint in this case is the magnitude constraint. So we want the squared magnitude of rho's Fourier transform to equal the measured diffraction intensity I. And we also have our physical constraint, or support constraint in this case, which is basically that the density has to be contained within some finite support region S in the real space domain. And so what we need to do here is we need projections for each of these constraints. So for the magnitude constraint, we have the magnitude projection, which just in this case corresponds to being renormalization of the Fourier transform so that it has the correct magnitude square root of I. And so visually, this corresponds to, for each Q point in the complex plane, projecting rho hat Q, which is just a complex scalar, to the closest point on a circle of radius square root of I. And then for the support constraint, we have the support projection. And all that does is it takes your current density and it zeroes it out everywhere outside whatever your specified support region is. So pictorially, this corresponds to taking your object or your density here in blue and whatever support you want to impose on it, and then just seeing where your object extends beyond that support region and just chopping the density off there. And so if you toss these projections into the alternating projection scheme I just showed you, you get the error reducing or AR method, where you just take your current density estimate and then apply the magnitude projection and then the support projection, and then just keep alternating between the two until convergence. And so this ends up being a good local optimizer. It's good at reducing the error in the system, but it tends to get stuck in local minima. So people tend to couple this with a good global optimizer, such as hybrid input-output or HIO, which instead adds this negative feedback term here in the bottom. And the effect of that extra term is essentially that which you compute outside the support is basically if you start to converge to something that's inconsistent with the support constraint, this negative feedback term starts to blow up and kick you out of that local minima. So usually what people do is they combine both, they sort of do several cycles where you do several iterations of HIO, then several iterations of ER, and sort of back and forth, so that you can both sort of escape local minima and reduce the error in the system. And so here's a simple example of that, just to sort of show how it works. So on the left is the diffraction intensity of a happy face. And then what we're going to do here on the right is we're basically going to alternate between several cycles of HIO and ER. And then we're also going to update the support estimate through a technique called shrink wrap, which I went into detail about yesterday, but I won't say too much about here. But basically, we're going to refine the support estimate as we go along. And then, so if we just let this run, then this is what we get. So you can sort of tell when you're in the HIO regions, that's when all this junk comes outside the support. That's the negative feedback blowing up and kicking you out of the local minima. And ER is when sort of all that gets cleaned up and you're sort of zeroing things outside the support. And then as you see, if we let this run long enough, it starts to converge to the face. And eventually converges to something that's pretty clean, as you see there. There we go. So it works there. So now what I want to talk about is how do we extend these iterative projection, iterative phasing schemes to more complex inverse problems. So basically the way we solve the phase problem is we came up with a projection we had a nice projection to deal with the magnitude constraint, the magnitude projection. In that case, you could compute it just as a simple renormalization in Fourier space, so it's easy to compute. But in general, we have to sort of figure out how to come up with a projection for this general data constraint, where we have this model M and it maps the data D through some mathematical operation F. And so we need to figure out if we sort of need a good fast projection algorithm to sort of pseudo-invert that operation. So given a model estimate M, we want to find the closest thing that correctly maps to the data D. And so for the phase problem, again, that was quite easy to do. But what if there isn't actually a good, efficient method for computing this projection? What do you do then? Because this is an essential part in getting these iterative projection, iterative phasing methods to work. And so what I want to propose here today is that if you don't have a good way to do this projection directly on F, maybe you can instead find a decomposition of the forward mapping relating the model to the data, where you express F as a nested series of functions. So as f of 4 of f of 3 of f of 2 of f of 1 of m. And then you can, of course, add more f's if you want. And you perform this decomposition in such a way that you try to have efficient methods to compute the projections for each of these f's. And so essentially what we're doing now is, instead of just treating the relationship between the model and the data as just one simple operation F, we're instead splitting it up. So now we basically have this representation here where we have our model estimate M on the left, the data D on the right. And now we're breaking up the relationship of the forward model. So basically, so now we're treating it as applying F1 to the model to get this intermediate quantity W1, then F2 to get W2, then F3 to get W3, then F4 to get all the way to the data. And so if you sort of think of things in this terms, you sort of have we're sort of replacing our simple data constraint of that we want to model M that maps the D through F in place of these 4 constraints here in the bottom, where we want to model M in a bunch of W's such that F of 1 of M maps to W1, F of 2 of W1 maps to W2, F of 3 of W2 maps to W3, and F of 4 of W3 maps to D. And so the hope is by instead considering these data constraints, maybe we have good ways to compute the projection for each one of these Fs, even though we don't have a good way to project the original F. And so this is sort of the basis of the what I've been calling the multi-tiered iterative projection or phasing scheme, MTIP. I sort of abuse the sort of notation for P to mean either projections or phasing depending on the context, sort of like the relationship between iterative projection methods and iterative phasing methods. And so essentially what you do in these MTIP schemes is you start by decomposing the forward computation relating the model M on the left to the model D on the right, like I showed you on the previous slide, where again, you get these intermediate model quantities, the W's. And so what we're gonna want here is we're gonna wanna develop a series of projection operators to essentially enforce consistency in this decomposition, as well as any other kind of physical constraints that you wanna impose on the model, like the support or positivity, symmetry, things like that. So essentially what we're going to do here is for each of these tiers, so say at the W3 tier, we want to develop a projection operator that projects a current estimate of W3 to the closest thing that maps to the data D through the F4 operation. And then we want another projection of W2 to project W2 to the closest thing that maps to W3, another projection to project W1 to the closest thing that maps to W2, and to project the model M to be consistent with W1. And so then essentially, once you have all these projections down, you toss them into this big iterative loop, just like standard sort of iterative projection methods, where in this case, you're essentially, you start with some kind of random initial model M at the top left. And then during each iteration, you apply the forward operations in your decomposition to essentially go all the way to the data, which sort of lands you at this W3 point here. And then once you're there, you apply a projection to project W3 to the closest point consistent with the data. So now we're essentially going to use these projections to essentially give us a way to sort of go backwards, how to update the base physical model M to be consistent with the data. And so then one by one, we're going to keep applying these projections to sort of go backwards. So once we project W3 to be consistent with the data, again, that gives us this, this Z3 term here at the bottom. And then we start going backwards. So now we project W2 to the closest thing that maps this up to Z3 through the F3 function. I'm sorry. And then we project W1 to the closest thing that maps to Z2. And then we map the previous model to the closest thing that's consistent with Z1. And that ends up giving us a new model estimate M tilde at this bottom left, which you then can impose additional physical constraint C through more projections. And you can do this through either the ER, HIO, or whatever kind of other iterative projection, iterative phasing, iterative scheme you want. And then once you're there, that brings you back to the beginning of the loop, and then you basically just iterate until convergence. So I sort of think the best way to demonstrate MTIP is just to go through a few examples. Unfortunately, this means I'm gonna have to skip on some of the scientific detail, but there's gonna be other talks later today going through that in more depth. So the first thing I'm going to talk about is an experimental technique called Fluctuation X-ray scattering, or FXS. This is mainly in collaboration with Kanapir Pandey, who's actually given a talk going through all this in more detail in the afternoon session at 1:30 Pacific, and also Peter Zwart, who are both at LBL. And so essentially what you do in these experiments is you collect a large number of X-ray diffraction patterns from a stream of particles. And you can either set up the stream so that the particle distribution is very sparse, so that you basically only hit a single particle for each diffraction snapshot. But the nice thing about FXS is it turns out that it also works if you have lots of particles in the beam at the same time, so that each diffraction pattern is some kind of average over all the over all the particles that you're imaging. One of the key things that you need to get this experiment to work is you need the pulse lengths of the X-rays to be shorter than the rotational diffusion times of the particles. And so essentially what that means is that you basically need when you do the imaging, you essentially need all your X-rays to sort of simultaneously come in, hit, and scatter off the particles before the particles have a chance to move or rotate within the beam. As this will essentially prevent some kind of rotational motion blur that you'd otherwise get in the data, which would turn the data into sort of something that's angular isotropic, like you get in small angle X-ray scattering in solution. And so what you do, the main thing that you compute from these diffraction patterns is something called a 3D angular cross correlation function. And so essentially the point of this is that each diffraction pattern you get, especially if you have multiple particles per shot, is again, it's sort of an average from the scattering of lots of different particles at lots of different orientations. So the way to sort of untangle all that is to first compute this 3D angular correlation function. And the way you do that is for each diffraction pattern you collect, you look at the signal between all pairs of rings at two radii, say Q and Q prime, and then you compute a cross correlation between the signal of those two rings. You do that for each image, and then you average over all images, and that'll give you a 1D correlation curve that looks like this for each of these ring pairs. And so this ends up giving you a three-dimensional function, one of these 1D curves for each of the two radii, Q and Q prime. And then what you do from here is you then take each of these 1D correlation curves and you expand them into a Legendre polynomial series. And in particular, the Legendre expansion coefficients that I've denoted by BLQQ prime here end up being very important. And in fact, you can sort of relate it directly to the underlying structure of your sample. And so you can sort of think of these coefficients as some kind of higher order spectral curves. And so in particular, if you set L equal to 0, you get the standard 1D Sachs curve that you would get in Sachs solution scattering methods. And this is something that Tom Grant's going to talk about in more detail later today, how to reconstruct something from this 1D curve. But in addition to that, if you increase the order L, you get these higher order curves as well. And in fact, BLQ, the BL terms aren't just 1D curves, they're actually two-dimensional functions of the two rings, Q and Q prime. So you actually get a series of 2D spectral surfaces, just not just 1D curves. Here I've just plotted them as 1D curves just to fit everything in the slide, but they're really 2D spectral surfaces. So you sort of really do have full 3D information there. But then the question is, how do you go from these BL coefficients and reconstruct the density of the sample that you're imaging? And so actually, this was sort of the main motivation for initially coming up with MTIP, how to solve this problem. And so sort of the problem here is that it turned out that the data projection that you would need to directly invert, sort of pseudo-invert the relationship between the model and the data was sort of too complicated to come up with a single projection for. So this is sort of what led into MTIP. And so again, what you do in MTIP is you start by decomposing the forward operation relating the electron density rho on the left to the data d on the right, which here I'm taking to be these Legendre coefficients, the spectral surfaces BLQQ prime. And instead of carefully going through the theory of how this is all derived, I'll just sort of tell you what this relationship is. So here the forward operations going from left to right include basically a Fourier transform, then a squared magnitude. So this first part is basically just like the phase problem. And so this ends up giving us a 3D intensity I. But then the third step is we take that intensity and we compute a spherical harmonic transform. If you're not familiar with spherical harmonic transforms, you can essentially think of them as just Fourier transforms on a sphere. They sort of have similar properties to the Fourier transform. So just like you compute a Fourier transform very quickly through a fast Fourier transform, FFT, there's sort of analogous fast spherical harmonic transforms as well. So we have a good efficient way to compute this. And then for the last step, it's to go from these spherical harmonic coefficients to the data. You can express it in terms of what's called a Gramian product. So essentially what I mean here is that if you take these spherical harmonic coefficients, which are indexed by these L and M, and they're also a function of a radius Q, you can express these as a series of matrices IL by essentially arranging these coefficients into a matrix where the rows are indexed by Q and the columns are indexed by the M. And then you can also think of each of these BL data as another series of matrices where the rows are indexed by Q and the columns are indexed by this Q prime. And so when you do that, you can actually directly relate the spherical harmonic coefficients to the data through this ground product. And so ground product just means you take each IL matrix and you multiply by its conjugate transpose, and that gets you to the data. So what we're going to need now is we're going to need projection operations for each of these for forward operations. So the Fourier transform, that's easy. It's invertible, so its corresponding projection is just the inverse Fourier transform. The squared magnitude is just the magnitude projection I showed you before for the phase problem. For the spherical harmonic transform, it also has a corresponding inverse spherical harmonic transform, and there's fast methods for computing that. And then the last term, the Grommen product, the corresponding projection is actually really cool, but unfortunately, I don't have time to go into detail about how it works here. The main idea is that you can express it in terms of an eigenvalue decomposition of each of these BL matrices, and then you have to solve something known as a unitary Procrustes problem, where you have to find some kind of unitary matrix UL that sort of optimally aligns the spherical harmonic coefficients to the data. And it turns out you can compute this very efficiently through a Singer value decomposition. But the point is that we essentially have sort of fast numerical methods for computing all these forward operations and all of these projections. And so then what you do from here is you toss them into this big iterative loop that I showed you before, where in this case, we're starting with a random initial density rho at the top left. We're computing its Fourier transform to get rho hat, then taking a square magnitude to get the intensity, and then a spherical harmonic transform to get these spherical harmonic coefficients I and Q. We then use the Grommen projection to project them to the closest thing consistent with the data, and then we start working ourselves backwards. We then take those new spherical harmonic, projected spherical harmonic coefficients and do an inverse spherical harmonic transform to get a new intensity function, and then a magnitude projection, which uses the previous Fourier transform or hat values to get a new Fourier transform, and then we invert that to get a new density in real space. And then we apply whatever real space projections we want to enforce things like a support or positivity, symmetry, so forth, again, through either the ER, HIO, or whatever kind of other iterative scheme that you want. That takes you back to the beginning of the loop, and you just iterate over this until convergence. And so here's some examples of actually using MTIP on experimental data collected at the LCLS. So at the top here are some examples where we applied MTIP to determine three-dimensional structures of two different viruses, a Rice-Dwarf virus on the left and a PR772 bacteriophage on the right, from single particle fluctuation scattering data collected at the LCLS. So here it was set up so that there's only a single particle in the beam at any one time. And this is what was done largely in collaboration with Ruslan Kurda at the European Expo. And on the bottom left, this is something that Kanapir Pandey is going to talk about in more detail later today. This is a reconstruction of a PBCV1 virus from multiple particle fluctuation scattering data collected at the LCLS. So here, for each diffraction snapshot, there were 100 different viruses in the beam, all at different positions and orientations. And so here, MTIP was also able to reconstruct the 3D structure of this virus, PBCV1, from the experimental data. So let's go through another example of how MTIP can be used. So here's another project I'm working on in collaboration with Zhang Zhang, Maoqi Chu, and Nicholas Swartz at ARPA National Lab. This is an experiment called Coherent Surface Scattering Imaging, or CSSI. And so what you do in these experiments is you collect diffraction patterns from a thin sample, looks like this, placed on a substrate. And so the thing is, since the object's really thin, if you shoot the X-ray sort of perpendicular to the surface, it turns out you don't have much interaction with the sample. You don't get much scattering off it. So what you have to do instead is you have to do the imaging at very shallow grazing incident angles relative to the substrate. But the issue that this causes is now you end up getting multiple scattering events due to additional refraction off the substrate. So basically what can happen is that when you shoot X-rays at the sample, the X-rays can either come in, hit the sample and scatter off, And this is what gives you the normal Born approximation or the Fourier transform of the density that you get in the standard phase problem. But in addition to that, the actuators can also come in, hit the sample, then bounce off and hit the substrate, scatter off to the detector, or it can go substrate sample detector, or it can go substrate sample substrate detector. And so basically for each of these additional scattering events, you kind of get an additional term in the formulation for the measured diffraction intensity. And this is something known as the distorted wave Born approximation, or DWBA. And so basically what this says is that the measured diffraction intensity is now the squared magnitude of the Fourier transform of your density. This is the normal Born approximation term that you just get in the normal phase problem. But in addition to that, for each of these other reflection events, you get these other terms, which consist of various translations and reflections of the Born approximation term. And then these are multiplied by what are known as Fresnel reflection coefficients, R1 and R2, which you sort of actually know if you know the sort of the makeup of the sample, what material it's composed of. So, so then essentially what you want to do is, well, if you want to sort of study the three-dimensional structure of your sample, you kind of need to do the imaging in a rotation series to collect 3D information. So essentially take your sample and rotate it, and then collect diffraction patterns from a bunch of different orientations of the sample. And that gives you a rotation series that looks like this, where again, you sort of get another diffraction pattern for each rotation of your sample. And then from this rotation series, you want to somehow combine this into a three-dimensional diffraction volume. And then the problem becomes, how do you go from this and reconstruct the density of the 3D density of your underlying sample? So let's see how to do this in MTIP. So in this case, here's our problem decomposition relating the density to the data. And so we go through these operations. The first operation ends up being a non-uniform Fourier transform. It's technically non-uniform because even though you can actually express the first Born term on a grid, it turns out that the other translations and reflections you need for the other components actually take you off grid. But the neat thing is it actually turns out you can still express that in a series of just normal Cartesian FFTs, but this time you have to do 4 FFTs, one for each of those reflection terms. And to deal with the translations and reflections, you have to multiply by various phase factors or reflections of the density in real space before you take the FFT. And so this gives you a sort of efficient method to go from your density to those 4 terms. And then the next step is just computing the squared magnitude of the sum of the 4 terms that I showed you in the last slide. And so now we need basically need projections for each one of these to sort of pseudo-invert them. And so for the non-uniform fast Fourier transform, it actually turns out there's another efficient way to compute its inverse directly. Again, just by computing normal Cartesian inverse fast Fourier transforms. But this requires you to, first you have to optimize the set of weights to actually make this the actual inverse of the Fourier operation in 1, that's these W's. And it also involves, again, multiplication by various phase factors and reflections. And again, the point is that you can sort of do this inversion very efficiently through just standard inverse fast Fourier transform. So it's very easy to do. And then for the projection for the second part, it ends up you can express that projection very efficiently through just a simple analytical expression that you see here. And so you can compute that very easily as well. And then just like before, you basically toss these forward operations and these projections in the same kind of iterative loop that I've been showing you. And so here's an example of actually applying this to some simulated data of the Siemens star on the left. And in the middle is the merged 3D CSSI diffraction volume that we throw into MTIP. And on the right is the reconstruction that we're going to get. So I start with basically just random noise for the density. So here I'm visualizing the density as a isosurface of the three-dimensional grid. So the initial random density actually ended up being too low. It was below the threshold I used to draw the density. So it just shows up this blank here. But if we let this run, you see that we sort of quickly converge to the structure of the Siemens star on the left. And so here's a more complex sample that I reconstructed as well. Unfortunately, I didn't have time to make a movie of this. So this was a reconstruction of a porous medium, where here the data was simulated through the ground truth object on the top. So it's basically just a cylinder with a bunch of holes cut out randomly. And on the bottom is the reconstruction, which has a pretty good match to the ground truth. All right, so that's mostly it. We've also extended MTIP to several other kinds of experiments as well. So this includes things like X-ray photon correlation spectroscopy, which Zisha Hugh is going to talk about next. To single particle diffractive imaging, which Ira Sheng is going to talk about at 11 Pacific today. We also did a recent project with John Spence on using some kind of MTIP-based scheme to invert data from multiple scattering electron crystallography. And I've also been playing around with using MTIP to try to come up with a better, more efficient way to train neural networks as well. And again, I'd like to point out that if you'd like to learn any more details about the fluctuation scattering stuff that I talked about before, then also please see Kinapura Pandey's talk later today at 1:30 Pacific. So I'd like to thank all my collaborators that I've listed here, and thank you all for coming today and for listening.